Greetings. Welcome to lesson 27. This lesson introduces the definition and equations of symmetrical components. In lesson 28, I will have some numerical examples. Symmetrical components theory was first introduced by Charles Fortescue in a paper that he published in 1918. His theory is considered by many to represent the most important advancement in electrical power engineering in the 20th century. Symmetrical components and sequence networks are commonly used in analysis of faulted three-phase systems. Consider the three identical phasors on the left. They are identical both in magnitude and their phase angle. They're called the zero sequence set of voltages. I'm using voltages for the definitions here, but they could have just as well been currents instead. The set in the middle is called the positive sequence set, and it again consists of phasors that are equal in magnitude, but they form a positive sequence set of phasors. If you start with VA1, you see that VB1 lags it by 120 degrees, and VC1 lags VB1 by another 120 degrees. So they form an ABC or positive sequence set. The last set, the one on the right, is made up of three phasors that are identical in magnitude again, but they form an ACB or negative sequence set, again starting from VA2. We'll see that VB2 leads it by 120 degrees and VC2 leads VB2 by 120 degrees. So therefore they form a negative sequence set of phasors. Each set taken by itself is a symmetrical set, which is where the name symmetrical components comes from. Notice that the zero sequence set is identified with an index that has a 0 in it. Positive sequence set has number 1 in its indices, and the negative sequence set has number 2 in its indices. This numbering system for the three sequence sets is industry standard. 0 for zero sequence set, 1 for positive sequence set, and 2 for negative sequence set. I'm going to add the A components from each set together to form a new phasor. So I'll be taking this phasor from this set, this phasor VA1 from positive set, and VA2 from the negative sequence set, and add them here graphically at the bottom here. So I'll be transferring VA0 from here to down here. Here it is. One more time just to see exactly where it's coming from. And I'm going to add the VA1 to it by putting the start of it to the tip of the VA0, something like that. And here it is, VA1 coming from here to down here. And now I'm going to add the A component from the negative sequence set to the sum of those two, graphically again, to find, and then find the total of the three added together. So here's the VA2 from the negative sequence set. And here are the three of them, end to end. Now if I connect the end of the starting point of VA0 to the ending point of VA2, that'll give me the sum of the three, which I'll call VA. And here's the sum graphically. And here's the sum as an equation. Next, I'll add the B components from each set to form a new phasor, which I'll call VB. So I'll take VB0 from that set, VB1 from this set, add it to it, and VB2 from the negative sequence set added to the other two. And then if I connect from here to here, that'll give me VB, the sum of those three. And here they are graphically and in equation form. And finally, I'll add the remaining phasors, which will be the C components, together. And starting with VC0, moving it to here. VC1 added to it from here to here. And VC2 will be added to the sum of the other two graphically. And VC is formed by adding the 3. Here's the VC in graphical form. And here's VC as an equation in terms of the C components. I'm going to start to add, not to add, but to translate these three phasors to a point here. I've already moved VA from here to here. I'm gonna put the other two next to it so that we can see them in one place and be able to compare them and see how they relate to each other. So VB, again translated to here, and VC translated to here. You can see that VA, VB, VC form a trio of phasors that are unbalanced set of phasors. Now, if the theory of symmetrical components ended here, it would not be anything special because you can pick 3 sequence sets at random, as was done here. And using their components, you can form 3 phasors, which themselves form a random set of 3 phasors. What makes the theory especially useful is that it shows how this process can be reversed, in the sense that given any trio of phasors such as VA, VB, VC, you can uniquely identify its 3 constituent sequence set. You can go from here to forming 0 sequence set, positive sequence set, and a negative sequence set, and that is done uniquely. What makes the sequence sets useful is that they replace the unbalanced set of phasors, VA, VB, VC, in the analysis of circuits. And since the 3 constituent sets are themselves balanced, they facilitate system analysis. We'll be using this set, and this set in place of these 3. The application of this theory to circuit analysis will have to wait until we get to the lessons on the topic of system protection. But let me now look at the inverse process of finding the sequence sets from a set of 3 phasors. This process is best explained with a little bit of algebra, so I'll delete the diagrams that we have here and keep the equations, these 3 equations. I would like to introduce a constant complex number with a magnitude of 1 and an angle of 120. This number is useful in this work and typically is given the letter A for its name. Here it is. We're going to need the square of A as well, so let me just form that here. A squared equals this number multiplied by itself, so it becomes 1 with 240 degrees. But if I take away 360 from the 240, I'm going to use this form of it, 1 with negative 120 as A squared. And here they are, A and A squared. What I'm going to do next is to use the A and A squared to replace these phasors, the B's and the C's, and express them in terms of the A components. So starting with VB1, you can see that VB1 lags VA1 by 120. So I can rewrite it as A squared VA1. VC1 leads VA1, so that can be written as A times VA1. And similarly here, VB2 leads VA2 by 120 degrees, so it can be expressed as A times VA2. And VC2 lags VA2 by 120 degrees, so that can be written as A squared times VA2. For the zero sequence set, it's even simpler. We keep VA0 as it is, and we replace VB0 with VA0 because they're equal both in phase and magnitude. And same with VC0 becomes VA0. And we'll make similar changes here. We'll keep the A components in each case, the A components which are here, and we replace the B components with their equivalents in terms of A components, and also with C components. We represent them as an expression that only has A components in them. I've done that on the next slide, so you can see VA doesn't change, it's the sum of those three. But for VB, now everything is represented in terms of VA0, VA1, VA2. And for VC, same thing. It's expressed in terms of sum of three phasors that are all expressed in terms of VAs, VA0, VA1, and VA2. In this way, we do not need the B and C indices in the equations or the sequence sets. Everything is now expressed in terms of those three, VA0, VA1, and VA2. So I'm showing that on the next slide. You don't see anymore the VB0, VB1, VB2, and neither VC0, VC1, VC2. Everything is set up in terms of the A components, A1, A2, and A0. I'll collect these three equations, put them all in one place so we can work with them. Here they are. The best way to, well, these are the three equations in three unknowns, and they're linear, and you can solve them in any way that you've seen before. But the most systematic way of solving them would be to put them in a matrix format, which I've done here. So I'll take these and make them into a vector, a column vector. Take the coefficients and make them into a 3 by 3 matrix, and take the unknowns. Remember, we're going to be finding these, and make a vertical or a column matrix, column vector out of those. To find these unknowns, VA0, VA1, VA2, we're going to be multiplying both sides of this equation by the inverse of this matrix. So we're going to need the inverse of that matrix, and here it is, pre-calculated, equals 1/3 times this matrix. As a practice, you should multiply this matrix times the original matrix, which is this one, 1, 1, 1, 1, A squared A, and 1A, A squared. And make sure that you get the identity matrix, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1. In doing so, you should remember that A cubed equals 1, A to the power of 4 equals A times A cubed, which makes it A times 1, which is A. And also you're going to run into expressions such as 1 plus A squared. But due to symmetry of these three, they fall like this. So their sum is going to be 0. I'm not going to carry out the multiplication of the two matrices. I'll leave that to you as an exercise. But I will multiply both sides of this equation, this matrix equation, by this inverse. So in doing so, this turns into an identity matrix, I3, and that will give me VA0, VA1, VA2 in terms of VA, VB, VC. And to see the relationship between the two sides, I'm going to expand the matrix equation into three different equations, and that's shown here. So you can see that if we have VA, VB, VC, the three phasors that we start with, we can find VA0, VA1, and VA2 from them, because these are just complex numbers whose values we know. And plug everything in here on the right hand side, and you find VA0, VA1, and VA2. So once we find the VA0, VA1, VA2, we can easily set up these three sequence sets. For the first one, everything is the same, so we have VA1, and the other two are exactly the same. For the positive sequence set, we just rotate each to get VB1, and 120 degrees again to get VC1. And once we have VA2, which again we'll find it from these equations, you rotate it in a positive direction, you get VB2, and another 120 degrees in a positive direction, you get VC2 out of that. It's a common practice to simplify even further by eliminating the letter A from the indices of the VA0, VA1, and VA2, and just call them V0, V1, and V2. When this symbolism is used, it's implied that we are talking about the A components of the zero set, of the positive set, and of the negative set, respectively. So here I'm showing them in terms of V0, V1, V2. See, V0 replaced VA0, V1 replaced VA1, and V2 replaced VA2, just symbolically. They still represent VA0, VA1, and VA2, but it's just easier to write down and work with. So in every case, I have replaced I dropped the A's, basically. And here are the equations to remember in going from three phasors, any three given phasors, VA, VB, VC, to their sequence components, positive, zero, positive, and negative sequence. We have reached the end of lesson 27. In lesson 28, I'll go over some examples that will provide practice with the use of the symmetrical components. My name is Fuad Alvandi. I am a PE electrical power engineer. You'll find my name, web address, and email address on this slide. Web address is own-your-destiny.mylearnedworlds.com, and email address own- spelled out, your hyphen, again spelled out, destiny@yahoo.com. I invite you to visit my website when you have the time. You'll find comprehensive modules on different topics of power systems engineering on that website. Thanks for watching this video, and I hope to see you soon in another one of my presentations.